And because that takes a couple of seconds for it to finally kick off.
Sure. We don't have a clacker. Clack.
We're good to go. So go ahead.
Good evening. Good evening, everyone. Our speaker tonight is NASA research scientist Dr. Kelly Fast, who has led multiple research and analysis programs in NASA. Her most recent as Planetary Defense Officer and manager of the Near-Earth Object Observation Program. The goal is to study and plan a response to the asteroid impact hazard. Their motto is finding them before they find us. Everyone, please welcome Dr. Fast.
Oh, thank you so much for having me. I'm so pleased to get to speak to this group. I wish I could have been there in person, but I'm so happy to speak to you now. So I'm going to go ahead and share this as we practiced earlier. All right. So my current title is I am actually NASA's acting Planetary Defense Officer for the Planetary Defense Coordination Office, which is part of the Planetary Science Division at NASA headquarters in Washington, D.C. For myself, I'm an astronomer by training, and I worked for many years as a research astronomer at Goddard Space Flight Center. And then for over a decade, I've been at NASA headquarters managing programs related to astronomy and also some missions. But then also for a very long time now, planetary defense and looking for near-Earth objects, asteroids and comets, finding them before they find us. And then I like to say maybe getting them before they get us if it comes to that. But I started as an amateur astronomer. I grew up in Hollywood, California, but I still had a telescope. I went out there and looked, and yeah, it's hard to find things, but you could find the planets, and that's where my passion ended up ultimately along the way. Though I was proud of myself, I could find the Ring Nebula with star hopping and averted vision in Hollywood, but it was a little tougher for the deep sky objects, but you could find the planets. And so it's kind of fun to now be involved in, I did a lot of solar system research, but now actually protecting the planets. And so thank you again for having me. And for this talk on planetary defense, so it's very timely actually, because this invitation came a few months back, and we got it all set up, and a lot has happened since that kind invitation. So I'm looking forward to sharing. I'll just start off with some video, which probably a lot of you have seen, from 2013 over Chelyabinsk, Russia, a very, very bright fireball. There's stuff that is hitting the Earth all the time, dust-sized particles and maybe even few meter-sized asteroids, and they just create shooting stars or pretty fireballs in the sky. But this was pretty significant. This was about a 20-meter sized asteroid that entered over Russia, created this very, very bright fireball, as you can see from the surveillance footage. And I don't have sound for this because we couldn't share it, but it also turned out that I didn't want you to hear all the Russian swearing, my Russian-speaking colleague tells me. And so the scenes with the shaking and everything, there was a blast wave, a shock wave that was emitted from the energy released from the disintegration of this asteroid in the atmosphere. And so the atmosphere did a good job for us. This did not reach the ground intact. It only reached the ground in pieces, but still all that energy was released, blowing out windows, blowing out that door there, as you can see. Nobody died, thankfully, but there were injuries due to broken glass. And this was a relatively small asteroid. But it was just a reminder. I mean, there were searches for asteroids going on before that. But as over time, as you're seeing in this video, as we keep searching for asteroids, we're finding There's more and more of these near-Earth asteroids out there, asteroids that enter Earth's neighborhood that come, within about 1 1/3 times the distance from the Earth to the sun. Those are near-Earth asteroids. There are asteroids that stay safely out in the main belt. But over the history of the solar system, like Jupiter's gravity and interactions and such have tweaked the orbits of all of these leftovers from the formation of the solar system, and they find their way into the inner solar system. It looks really busy in this image here at the end, but really each of those dots, you wouldn't even be able to see them if we made them the actual size. Everything is very, very far away. The odds of things coming together in the same place at the same time are pretty small, but it can happen. It's happened throughout the history of the solar system. And then in the case of Chelyabinsk, we saw that happen. We see the craters on the Earth, the craters on the moon. It has happened. It will happen again. And so if we can actually predict it, if we can find these asteroids and know where they're going to be in the future, that's a very powerful thing, because it's the one natural disaster that you could potentially prevent. And so that's why NASA is doing this. NASA's work in this area goes back to the late 90s, funding near-Earth object observations and research. But in 2016, this was formalized into the Planetary Defense Coordination Office, just to manage those ongoing asteroid research activities, but then also the coordination both across the US government to other agencies, and also with our international colleagues to study and plan the response to the asteroid impact hazard. And so our role is to lead those national and international efforts to detect any potential for significant impact of Earth by natural objects. So asteroids and comets, we're just dealing with the natural objects, the finding them part. Appraise the range of potential effects by any possible impact, to understand what could happen should something impact the Earth, depending on the properties of these bodies. And then develop strategies to mitigate impact effects on human welfare, be able to predict the time and the location, be able to convey information to other agencies like emergency response, but then perhaps even develop capabilities to avoid an impact altogether. And so that's all rolled up under this office at NASA. And it's not just a NASA thing. There actually is a national strategy, a national preparedness strategy and action plan for near-Earth object hazards and planetary defense that was developed under the White House Office of Science and Technology Policy, that actually lays out the responsibilities and the roles of agencies across the US government. NASA obviously has a very large role because we're the ones who coordinate the kind of all that initial information, the finding them, the assessing the hazard, potentially addressing, the in-space response. But there's roles for many other agencies also in terms of research or assisting with the response, or like in the case of emergency response, if should an impact happen within the US, or the State Department for something outside the US. So there are goals in the strategy and action plan for enhancing our capabilities to find asteroids and characterize them, the technologies for reconnaissance and mitigation, working on cooperation, the emergency procedures, and just improving that US management, across the interagencies, so that we really everybody understands their role and continue to keep things moving forward. But back at NASA, at the Planetary Defense Coordination Office, now for any of you who are Star Trek fans, I'll have to mention our shield there at the top for the Planetary Defense Coordination Office. If you're a Star Trek fan, this was actually designed by Michael Okuda, who did graphic design for a lot of the Star Trek series. And so that was a really cool thing. Me being a major Trekkie, certainly it was a wonderful thing for him to have done that for us. But looking here kind of clockwise, these are the areas that we address in the Planetary Defense Coordination Office. And that first one there is really kind of the meat and potatoes of it all. Search, detect, and track. You can't do anything about asteroids and comets if you don't know where they are and where they're going to be in the future. So finding them and tracking them and calculating their orbits. And then also you'd want to understand their physical properties. That's characterize. What are they made of? Are they rocky? Are they metallic? What are their sizes, their shapes, their other properties? Planning and coordinating, like I was just mentioning, across the U.S. interagency, but also with our international collaborators to be able to respond to a potential impact threat. Mitigate, be able to explore technologies for perhaps avoiding an impact altogether, or doing coordination on emergency response, or also reconnaissance missions, hopefully avoiding this altogether, and then assessing where we're at. How have we done with finding these objects and at least retiring the risk from some of them? You probably heard a few years back about the DART mission, which was a chance to kind of test one of those mitigation options to deflect an asteroid in space. And this was done with a binary asteroid, Didymos and Dimorphos, because this was it was kind of a natural laboratory type situation where it passed close enough to Earth where you could see the light curve coming from this asteroid, where the combined light going up and down as they pass in front and behind. And then if you took that spacecraft, the DART spacecraft, and then impacted it into that smaller asteroid Dimorphos, that slowed it slightly and dropped it into a different orbit around Didymos, changing the orbital period. It was changed by like a half an hour. But this was a test to say, okay, we the physics, if you hit something with something else, you're going to transfer momentum, but there's actually doing it with a real object, a real asteroid with real properties, with the regolith on the surface, that if that is ejected by the impact, actually gives it a little extra push. And so telling us more about, if we had to ever do this for real, here's how at least this particular technique, the kinetic impactor, how it would behave. Now, this is kind of fun. This is the approach. You saw Didymos on the side there kind of disappear, and this is Dimorphos. This spacecraft had to do one thing. It had to hit the right asteroid. It had to guide in on the right asteroid and then just impact it. And it sure did that. And you can see here with that very last frame, it was sending that last frame down to Earth when it impacted and it stopped. Normally, it would be a sad thing to lose a spacecraft, but we were all cheering because it meant that at least this part was successful. The impact was successful. And actually, the deflection was successful too. But again, you can't do anything about an asteroid that could potentially hit the Earth. You can't do a deflection like what was done with the DART mission if you don't even know enough about the asteroids that are out there, and if you can't find them first. And this is kind of fun talking to an astronomy group, because it's a group that really appreciates astronomy. And so here are the telescopes that we use for surveying the skies and first detecting these moving objects against the stars and trying to determine, okay, is this something we already know about? Is this something new? Is it an artificial object? Is this an asteroid, a near-Earth asteroid that has yet to be in the catalog and we need to track it more? We had actually a repurposed astrophysics mission in space, the NEOWISE mission. It was started as WISE, the Wide Infrared Survey Explorer, and it was used. It was studying things outside the solar system, but of course, asteroids are great photobombers. And as the mission was being developed, there was a team that looked at how can we pull asteroid data out of this too. And it ended up being very valuable, really, because it was in the infrared and it was able to return size information. But it re-entered the atmosphere last year on November 2nd. The mission wrapped up last year. It re-entered November 2nd. And so that one's wrapped up, but it was very, very valuable and a valuable pathfinder for a mission that's in development to do this in a targeted way. But our workhorses for finding asteroids, both for NASA and around the world, the two major surveys are the Catalina Sky Survey of the University of Arizona and the Pan-STARRS survey of University of Hawaii. Those telescopes are producing most of the discoveries around the world. The Atlas telescopes of the University of Hawaii are also producing discoveries. They're smaller robotic telescopes that are made to survey the sky quicker to maybe find what might have fallen through the cracks of the other surveys that are taking the time to go very deep and faint, whereas Atlas is searching quicker and catching maybe the brighter objects, but covering more of the sky quicker. So very complementary. We also collaborate with the U.S. Space Force and the Royal Australian Air Force on the Space Surveillance Telescope, which the Linear project at MIT Lincoln Labs pulls the natural object data out of the data that's used for other purposes. And so these are at least NASA's major survey systems. But of course, there's a lot that happens afterwards. And my son played lacrosse, and yeah, making a goal is important, but the assists are really important. And this is kind of all about the assists. The follow-up after something is first discovered, or before it's even known for sure that it is a new discovery or a new natural object, these telescopes go and they get additional observations of asteroids or potential new discoveries. Because, if you have a point in space, you can draw any kind of line through it. You need to have enough observations over a long enough time to be able to know how it's moving now and be able to track that into the future and to have an accurate idea of where an object could be in the future. So you can see, the range of telescopes, and this isn't even exhaustive. We have others, and then we also coordinate with colleagues around the world who continue to follow up the asteroid discoveries. So how this all works is that these position measurements of near-Earth objects and actually any small bodies from NASA projects and projects around the world are fed in to the Minor Planet Center, which is it's located up at the Smithsonian Astrophysical Observatory on the Harvard campus. But it's the International Astronomical Union's recognized repository for small body measurements from around the world. So they take that from everywhere. It's a very, very critical database. And they're responsible for the identification and the designation and initial orbit computation. They determine whether something is a new discovery or not, and they assign the designations, the number letter combinations to it. But the Center for Near-Earth Object Studies out at the Jet Propulsion Laboratory, they take all of those position measurements and they do the high precision orbit determination, both in the short term to see if something, a potential new discovery, even before it's been confirmed, does it pose, an impact threat? Is there something that could be an impactor? We don't want to take the time to not try to calculate it right away. But then also in the long term, they have their Sentry system takes orbits of asteroids and propagates them way out into the future, a century into the future, to determine could something pose an impact threat in the future. Often it's not necessarily what you see in the movies where it's making a beeline for us, it's going to impact right away. Where we're playing the long game, we would like to find these, maybe many times around the sun before they would actually impact. And so, and in the event that something is discovered that could impact Earth, the folks out there at CNEOS would determine the time, the location, and the geometry. Where would it impact and when? And again, that's a very powerful and empowering thing to be able to do. Also, we have some capabilities for studying the physical characteristics of asteroids and comets. And there are many other telescopes, universities and around the world that do that as well. But there are two NASA-owned facilities, NASA's Infrared Telescope facility on Mauna Kea in Hawaii. And before I became a bureaucrat and I used to be an astronomer, that was the facility that I used a lot. And And that's one that NASA makes available to the public for studying objects in the infrared and for doing spectroscopy and photometry. But then also Goldstone Planetary Radar on NASA's Deep Space Network on one of the dishes there, actually a couple of dishes, but there's one that's truly the high-powered interplanetary radar, because if something passes close enough to the Earth and you can bounce radar off of it, you can really narrow down, you can get its orbit very well. You can even get imagery of asteroids. So radar is a very powerful capability, and this is currently the most powerful radar in the world. I mentioned that we also work with our international colleagues, and there are two bodies that were recommended by the UN, these two collaborations for working together on the asteroid impact hazard. One of those on the left is the International Asteroid Warning Network, which is coordinated by NASA. In fact, I serve as the coordinating officer right now, and doing kind of that work that I just talked about, but on an international scale, searching for asteroids, following them up, getting their positions, getting their properties, determining their trajectories. All of that is rolled up under the International Asteroid Warning Network, and we have I forgot how many. I think we're getting close to 70 signatories from like over 25 countries. So really a lot going on there. And then also its companion group is the Space Missions Planning Advisory Group, and that's the forum for the world's space agencies and offices to come together to look at potential deflection mission plans. Now, obviously, budgets are handled by individual countries and strategies and all that, but what this group is to come together to be able to make recommendations on how to respond to a particular asteroid threat. And so to have that kind of communication and to kind of lay that groundwork ahead of time is very valuable. That's chaired by the European Space Agency. In the event of a credible threat, the International Asteroid Warning Network would inform the Space Missions Planning Advisory Group so that they can consider how to act. And also they would inform the UN through the Office of Outer Space Affairs so that the UN could then disseminate that information to UN member states. While at the same time, NASA, we have our own notification policy for disseminating information throughout the US government. So there's been a lot over the last decade put into place, just to make sure that it's not the first time that we've thought through something like this, even though an asteroid impact is a very rare event. It's low likelihood, but it could have high consequences. So where we are with the survey, these aren't all asteroids, but these are asteroids 140 meters and larger, because it's kind of a mix of things. It's what Congress has directed NASA to find. We want to find all asteroids, but it's a metric for setting, for looking at how have we made progress. The original metric was 1 kilometer and larger, and most of that population has been found. And so now the metric is 140 meters and larger, because that's still a size that could pose regional consequences should they impact. And so over the years, you've seen we developed better capabilities for finding these asteroids. And I mentioned the Pan-STARRS and Catalina surveys. Those are the pink and green colors there that are finding most of the asteroids. But you can see how things are kind of trailing off there. We're not finding as many each year with our current capabilities. And in fact, so we really have to wait for the asteroids to come to us. And this is where we are. We were supposed to be further on this goal, and we're not. But the thing is, and it would take 30 years with our current capabilities to reach that 90% level that Congress set for NASA many years ago. But we are making progress, both with improvements to the current surveys, but also because NASA does have a plan. So hopefully you can see on the screen there's 2 asteroids of the same size, one brightly colored, one darkly colored. And if you put them way out in space, the light they reflect is very different. How do you tell the size of these? If you could turn on your infrared eyes, all of a sudden that surface coloring doesn't matter anymore. It doesn't matter how much light it's reflecting. It's not as important. And it's harder for them to hide. And even if something is a very low albedo or darkly colored asteroid, as you see on the right, it pops out in the infrared. And so that's a capability we want to take advantage of. It was demonstrated on the NEOWISE mission for other purposes, but we want to utilize that capability in a targeted way. Area of opposition to the right there on your screen, that's where ground-based telescopes are looking. That's where you're going to be looking in the telescopes tonight, hopefully, if it's clear. The NEOWISE mission had this very narrow field of regard as it went around the Earth, and it would kind of sweep out the whole sky over 6 months. What NASA is developing is the Near Earth Object Surveyor mission. It is a space-based infrared telescope that's actually designed, not to do a whole wide range of science. It is designed to find the potentially hazardous asteroids, the ones that could come close to Earth's orbit and could potentially pose a hazard to Earth in the future, and that are of 140 meters in size and larger, and to speed up the rate at which we're finding things. And it is going to be positioned at the Sun-Earth L1 point, the Lagrange point. It's kind of a stable point between the Earth and the Sun. And you probably had heard before about the James Webb Space Telescope, that's out at the L2 point. This will be at the L1 point between the Earth and the Sun, operating the infrared, but passively cooled. So it gets it kind of away from the Earth, away from the heat from the Earth, but it also puts in a position to be able to survey along Earth's orbit and find the asteroids that come close to Earth's orbit. I mean, that can be done from opposition as well, because the asteroids are obviously going all around, but to be able to really target the ones that come close to Earth's orbit, to be able to look closer to the direction of the sun than is possible from the ground-based telescopes. So very complementary and powerful working together, and to be looking in the infrared. And so that even that lower albedo, that darker population, harder to find. And so this should really speed things up. It's currently targeting a September 2027 launch. And so detect to protect. And so this will be a way to, to even better retire the risk from some of these asteroids. Now, I mentioned we do get impacted, and we have some things happen that are actually, it's a good test of our system. And this one was in September of last year. There was a small asteroid. You can see the orbit that this asteroid was on, and the blue is the Earth's orbit where they came together. And this was, stuff hits the atmosphere all the time. The smaller stuff, when there's more of the smaller stuff, so it's more likely to happen. But thankfully, again, our atmosphere helps to take care of that. But it's not often that something is discovered before it impacts. This happens, you see a fireball, but to find it ahead of time, and you can see the discovery observations on the left there from the Catalina Sky Survey, and then the predictions by the JPL Center for Near Earth Object Studies. They predicted an impact, but it was unclear exactly where it could be. It got narrowed down to this region here, off of Southeast Asia. And then with more observations, it got narrowed down to just off of the coast of the Philippines, off Luzon. And then sure enough, people saw a fireball. We put it out on social media. Our ESA colleagues put that out on social media, could tell people, if you look in the sky in this direction at this time, you will see this. And sure enough, people saw a fireball. And so it was a good test of our capabilities to say, okay, we can trust what is coming out of our prediction software, of the orbit software. Very good test. And it was on kind of a short turnaround, just found a few hours beforehand. But, the small stuff, you don't see it till it's really close, and it's not a hazard anyway. But if we would want to find something years ahead of time that could pose, an actual damage hazard to the Earth. And we do try to exercise some of these capabilities too on an interagency scale. And this is something we had last year. We had representatives from across the government, and not just from NASA, but from FEMA, who was one of the organizers, FEMA and NASA together, State Department, the Space Command, we had the National Science Foundation, national labs, U.S. Space Force. We had, but we also had our international colleagues from UN Office of Outer Space Affairs, European Space Agency, the collaborations I mentioned, International Asteroid Warning Network, Space Mission Planning Advisory Group. So we do try to work through scenarios saying, okay, you have an asteroid that's been discovered this much ahead of time, and this is what you know about it. in this, we'll drop into this point in time. What do you do with such a situation? So we've done these a number of times, and these exercises have gotten larger. They also happen on an international scale through our planetary defense conferences. But we had a chance to exercise this recently, and you probably heard about this in the news, or some of you may have heard about this. So there was, we had an asteroid that, again, I just showed that one that impacted off the Philippines that was small, wasn't a reportable one. This was one that was at the size that at NASA, we're required to report through the government, and that also we reported as part of our role with the International Asteroid Warning Network, reported to the UN. So this asteroid was estimated to be about 40 to 90 meters in size, and it was first reported to the Minor Planet Center on December 27th, just after Christmas, by the one of the Atlas telescopes of the University of Hawaii that we fund, the station that's in Chile. But it reached an important threshold. It surpassed 1% probability of impact in January, and we saw it climbing that way. That sounds very small, but it's rare for something of that size to even reach that level. And it's a level that we've kind of established, through many conferences and studies, and looking at what makes sense to start, to really be paying attention. And this is a level that you don't want. You want to make sure you're already tracking this. So it surpassed that 1%. And then it reached a maximum probability of 3% on February 18th. And then soon afterwards, NASA ruled out any significant impact threat. And it seemed to happen very quickly, but there's a reason why, which I can show you. And all of the data were public. You might have seen it bubbling up there. Even in that run up to 1%, there, information was out there because the data were public. But we were taking the time to make the observations. And then once we hit that 1%, that's where we do our required formal reporting. And so it was the first time ever that had happened since these bodies were set up, the International Asteroid Warning Network, and also since NASA set up its notification policy in the government. So it was very significant. Oh, and then here's the slide on notifications. So it did surpass 1%, and that triggered this formal notification to the U.S. interagency per our policy directive. And at the same time, we, on behalf of the International Asteroid Warning Network, notified the Space Mission Planning Advisory Group and the UN Office of Outer Space Affairs, who then sent that information through their circulation mechanisms. It wasn't anything for anybody to get upset about. It was just, we are conveying information, being very transparent about it. And it actually went very well, because we have been, this has been something that's been reported. It's one of the sessions at the UN Committee for the Peaceful Uses of Outer Space, their scientific and technical subcommittee. We've been reporting out for years there. And so it was not an unusual thing to see, which was great to hear, even though it was the first time we'd ever reached that threshold. And so here's how things played out. As the telescopes on the ground here were continuing to observe, where the asteroid was calculated to be in 2032, that uncertainty shrunk. You see right now, it could have been anywhere way out beyond the moon, or it could have been dead on the Earth, dead center there. And then as new observations came in, that uncertainty region in 2032 shrank. Now, as the uncertainty shrinks, the probability for the Earth is going to go up. But we didn't know for sure that whether that probability would drop or not. So we had to keep tracking it. It went up to as high as like 3%. And then it started to drop because that uncertainty region shrunk off of the Earth, which was a good thing, but we wouldn't have known if we didn't continue to track it. And it turns out that even though the probability of hitting the Earth has gone way, way, way down, it's insignificant now. The moon is still in play. The moon still has a couple percent chance, about 2% chance, last I saw, probability of impacting the moon. on December 22nd, 2032. So we'll see. The same thing might happen where as more observations are made, that uncertainty region will shrink off the moon, perhaps. But it's an interesting thing. Now it can be like an interesting science endeavor, continue to watch that. But the James Webb Space Telescope did observe the asteroid, and they're going to be taking some more observations. They weren't able to do the types of observations to try to constrain the size using infrared, because right now we said 40 to 90 meters. You know, maybe it's towards one end or the other, but that's going to continue even though there isn't a threat to the Earth anymore, because it's a good chance to exercise all these capabilities. So again, if this pops up for real, they can do that. And but there was a really good chance for us to exercise the system in a way that you can't even do in an exercise, a tabletop exercise where you start with that notification. So it was really valuable. One other thing I wanted to mention, which again, this is astronomy group, so you may already be aware, in 2029, the asteroid Apophis is going to pass very close to Earth. It's like a 340-meter asteroid, and it is, and stuff passes close to the Earth all the time. Asteroids pass within the distance of the geosynchronous satellites, fairly often, but to have something that large pass within the distance of the geosynchronous satellites is pretty significant. And 20 years ago, Apophis, it was the same situation where it rose on the risk list, and it was thought that it could impact the Earth in 2029 or at a later time. But a few years ago, with actually one of the observing campaigns that we had with the International Asteroid Warning Network, got enough information on one of its apparitions to be able to kick it off the risk list altogether. So now it's a neat science opportunity, and it's a neat outreach opportunity. And your organization could be very active in that as well, because the UN has declared that 2029 will be the International Year of Asteroid Awareness and Planetary Defense. You might have taken part in the International Year of Astronomy a number of years ago. And so this will be another chance to kind of promote awareness of this topic, and to be able to do public outreach. So hopefully this will be an empowering thing for your club as well in 2029, to have this international year. And so we're looking forward to seeing this ramp up. I'm going to ask folks there to show a trailer. The other thing that's coming up in less than a month, we had started a small effort to put together some YouTube videos on what actually happens with planetary defense. You know, in the movies, it's like there's one scientist out there trying to warn everybody. Really, it's a whole system like I told you about. But it was a chance to kind of highlight some of the folks out at the observatories doing the work, the folks doing the orbit determination, these exercises, NEO Surveyor and DART. And so as we were putting this video together, the NASA Plus streaming platform was established. And so this was, and plus there was more material than to cram into like a few minute YouTube video. And so there's actually going to be a full documentary premiering on April 16th on the NASA Plus platform. It will also be on YouTube. But if you have any other streaming services, you can just punch in on your television, look up the NASA Plus platform. It's free. Before we go to that, so we'll show that short trailer, and then I'd be happy to answer questions, but I'll just put this up here briefly. We do have a website, nasa.gov/planetary defense, where you can see all of what I talked about, some summaries of what the things that we fund, and the what falls under this office, and some other things. The Planetary Defenders documentary page is there in the middle, and then also NASA's DART mission. You can go to that website there. Also, there's social media listed on the bottom. The one in yellow there at Asteroid Watch is NASA Asteroid Watch on the X platform, and that's where we put out posts about some of those imminent impactors, like those small impactors that we talked about there, or other things that are of specific interest to planetary defense and asteroids. We don't post as often as the other NASA accounts, but use that more for conveying that kind of information. So with that, I think I will go back over here and stop sharing. And if I would ask if you could play, if it's easy to go ahead and play that short trailer for the documentary. And then after that, I'd be so happy to answer questions.
Yep, I'll get that started now.
Thank you.
It can show up anywhere in the night sky at any time. Oh, this might be something. Oh, you guys, look at that. Right now, it is absolutely a potentially hazardous object. You guys are gonna be here for a discovery at PHA, definitely what you want. This is a big rock, yeah.
What would an asteroid that is a kilometer in diameter, what would it do if it hit the Earth?
That is likely to end human civilization.
Those objects are big enough to cause what we would call truly global devastation, meaning that they could cause global extinction events. The good news is that we found more than about 95% of them. When we get down to smaller objects, things that are larger than, let's say, about 100 meters across or so, now the picture's not so rosy.
Today, we do not have a complete inventory of all the possible impactors.
That could do regional damage should it impact Earth. A city killer.
We know of about 40% of those objects today.
And that is something that NASA and the worldwide planetary defense community has been endeavoring to do.
And there's a huge community of astronomers that start observing it from all around the globe.
Finding asteroids, tracking them, calculating their orbits, figuring out where they're going to be in the future, studying their physical properties, and then you get that information you might need in the event an impact threat is discovered.
Asteroids don't care about international boundaries.
It doesn't matter where the asteroid impacts. It affects, the entire humanity, in fact, anything alive on the Earth. It transcends basically anything except what makes us human and what it means to help discover and protect the planet from a hazardous asteroid that might be incoming.
I really like that I'm protecting the planet.
Let's say we do find something that poses an impact threat to Earth. What next?
The day is coming and Earth will get impacted.
The dinosaurs went extinct because they didn't have a space program. We do have one.
We can. So why stop there?
Okay, I got to see it.
Okay, thank you so much. So that's Planetary Defense at NASA, and you'll be able to see more when Planetary Defenders is released next month, and then always on our website and more. So if you have questions about what we're doing at NASA, be glad to take them right now. But thank you again for the kind invitation, and I'm really hoping one of these days to make it up there in person. That would be a lot of fun.
That would be wonderful. That'd be great. It's actually, I thought I saw somewhere that there's an asteroid with your name on it.
There is out in the main belt. It's actually not too uncommon. There are a lot of asteroids, and so, but actually a colleague in that trailer that was shown, the one that said, the dinosaurs didn't have a space program. We do have one. One of his asteroid discoveries, he had that named after me, which was quite an honor. And so I do. There is a Kelly Fast asteroid, but it stays safely out in the main belt. It's not one of the, the hazardous
darn well
ones.
better.
Yeah, right.
How, Len, do you mind if I ask some questions?
Go ahead. Does anybody have any questions here that they might want to ask? Okay, we got one. Go ahead.
Good. Go ahead with that one.
So you mentioned, I think the ESA is part of the agencies that would defend Earth. I guess they would create some sort of spacecraft to intercept the asteroid. And what is like the turnaround time for that potential resolution?
Okay, it was a little faint. I think I got all that. It was about like how long would it take to do, like if we found something that was a threat, how would we launch a mission, and what would be the turnaround time? It can take it does take years to put a mission together. It doesn't just happen overnight, and so it could take 5 years, let's say, to design and build a spacecraft. And then there's also launch opportunities because you have to kind of find the right time to lob something out at an object, especially if, let's say you found something that posed a threat and it was it had a few more times around the sun and playing that tag with the Earth before it would impact, but you'd have to find the right time to launch it. And so the tabletop exercise that I showed there was a 14-year lead time, which sounds like a lot, but as you start discussing things, it's actually that could be a challenge. And with 2024 YR4, we were finding something that could impact in 7 years, and that was really challenging too, because that wasn't that far out to be able to build a spacecraft. So it can be done. There are those who say, should we maybe have something that's, sitting on the pad ready to go? This may never really happen for real in our lifetimes. There's like the cost benefit of that. You got something sitting there that could, like, the technology goes stale and everything. And it also depends on the asteroid, how big it is, what is the lead time, what are the launch opportunities. So there's a lot of work that goes into studying what you could do to deflect an asteroid, because a kinetic impactor like the DART mission isn't the only way. There's some other techniques. How many might you need if you had a larger asteroid? But it's what we would like to look at is, rather than like building something to have it sit there, is how can you do something quickly? Or in the case of, I had mentioned like the deflection missions, if that's what it came to, but if you had years or decades of notice, you could actually send a reconnaissance mission ahead of time and actually study the asteroid. When you saw with the DART mission and you saw that approach to past Didymos to Dimorphos, and it's getting bigger and bigger there, that was the first time we'd ever seen it close up, and then we were impacting it. And so you could see how if there was the time to be able to launch a mission to study an asteroid and then launch something to deflect it, you could really then customize it and design it. So it's a really long answer to say it really does depend on the asteroid and on the scenario. But regardless, it takes like, at least 5 years to design and put a mission together. And one thing we do want to look at is like rapid response capability, which is something that's been identified like in our planetary science decadal survey out of the national academies and in our national strategy and action plan. One of the things that would be good to develop that kind of capability, and looking at, there's what you would want to do for asteroid science, but then what is kind of the bare minimum that you need for planetary defense. So anyway, long answer to that. It kind of depends, but it's not something that happens on a dime.
So what we could probably do is if we detect one, we could then mine it to oblivion. That would be the one that we would chop up and send up in pieces.
Yeah, if you had enough time.
Yeah, had enough time.
Will we need Bruce Willis to pilot the mission?
Yes,
Apparently.
yeah. Sort of tied into that is how often do you revisit these? I saw hundreds and hundreds that you're tracking are out there. I also saw the bar graph. Now the bar graph is that also rediscoveries?
That was just, the bar graph was just all the discoveries, and those were just the 140-meter and larger asteroids.
New ones? Oh, new ones.
Yeah, right.
Oh,
And then, but
wow.
still, like every time they come around, sometimes there are ones, we have asteroids on our risk list, kind of like that 2024 YR4 that we had, that we just had, that rose to the top of the risk list. There's other asteroids there, but they're down there at like, I don't know, 10 to the minus fifth chance or 10 to the minus sixth chance of hit, very low probability, but still they're not kicked off the list. And so sometimes like when those come back around where they're observable, that's one of the priorities that those follow-up telescopes, they will go try to get more observations of those asteroids that are on the risk list to maybe then kick them off altogether. There are things when they're first discovered, they pop on the risk list and those additional observations pop them back off right away. We just had a case where it didn't happen with YR4. It took a lot longer and it rose a lot more. All that's to say, and then the surveys continue to pick things up. Whenever the survey telescopes are observing, they're seeing known mate belt objects. They're seeing near-Earth asteroids that are already known. They're seeing ones that aren't known. All of those positions are reported to the Minor Planet Center, and they continue to they're used to better refine orbits of everything into the future. So those revisits are important, but they weren't rolled up in this discovery statistics, but the revisits are very important.
I see. And when, I know it was just 20 meters, but when Chelyabinsk, the Russian asteroid, showed up rather suddenly, did everyone go back and take a look to see what they missed on the charts or in the photos?
I'm not sure if they did with that. The problem is with Chelyabinsk, 20 meters is really small. That is
Small.
that's hard. I'm sure they did, but the surveys weren't as extensive at the time either, but I'm sure they did. But it's a tougher one, and it was on an orbit that was, and obviously it wasn't seen on its way in because it came from
Yeah.
the daytime sky. But that was done with 2024 YR4 because we had it was observed here in 24 and 25, and we knew that way out in the future, I should do it with this hand, way out in the future, it could impact Earth in 2032. But if we could have extended that into the past, that could have nailed 2032 a lot quicker. And there was a search that we went into the older images. And the problem is when 2024 YR4 has come into the inner solar system in the past, we haven't been in the right place at the right time to be able to see it well. It's been too faint. There was like a window in 2016 where it was kind of like on the border of where maybe some of the surveys could have observed it. And they all went back and were looking for, we call it pre-coveries. They were trying to look in the old images to see, was it there and maybe not picked up because maybe it was very faint, tough to see, it wasn't a good observation that you would have submitted then, but now we're looking for this. Can you nail that down? Nothing was found. And maybe over time something will be, because just like the uncertainty in the future is large, the uncertainty in the past is large too. But that is another important piece of the puzzle, is when new things are found, especially something that could, that is a higher interest object, like something that's a potential impactor, to try to go in to those past images, which now we have a lot more of, to be able to try to see, is there something in there? Was it maybe on the hairy edge? So, yeah.
Is there on the side sort of a group that just look at possible lunar impacts?
Well, the JPL team, the Center for Near-Earth Object Studies, they do look at, any kind of interactions, because as part of their orbit determination, they need to know if a small body is going to approach Mars, approach Venus, anything that could change its orbit. Even like Apophis, when Apophis approaches Earth in 2029, it's going to pass so close to Earth that Earth is going to change its orbit, and it's going to drop Apophis into a different orbit. And kind of like with gravity assists with spacecraft, that they go they come back by the Earth or go by. We had some spacecraft that just did gravity assists off of Mars recently. All of that's to say that those sorts of encounters are important. And I'm losing lock on the original question, John. What was
Only that if there was a group on the side that are just
Oh,
focusing
yes.
on lunar.
So it was, so they do have to look for any encounters. And so there isn't like a lunar impact page or anything, but the Center for the Near-Earth Object Studies is still looking at that for YR4 or anything. And that's how it was the JPL team way back when that identified, Comet Shoemaker-Levy 9, hitting Jupiter. In fact, Paul Chodas was part of that, and he's still at the Center for Near-Earth Object Studies. So as part of just their work with determining the dynamics of all of the objects in the solar system, they're always looking for those encounters, and they'll certainly fight, because it's of high scientific interest if something is going to hit. Even like a few years back, comet sighting Spring was on its way in, a long period comet, and it wasn't going to impact Mars, but it came very close to Mars. And I was involved with the Maven mission at the time, and there were all these, trying to make decisions about, okay, do you put extra blanketing on it ahead of launch, protect it from the dust that's going to be coming by at 52 kilometers per second, or what? And then they ended up just moving all of the spacecraft to the other side of Mars as the comet passed. But they do monitor all of that just to be able to do their high precision orbit work. But then it'll also flag, okay, here's a possible impact situation.
Wow, fascinating stuff, really. Okay.
Yeah.
Len, do you have other questions?
Does anybody? Yep.
How did you guys settle on 140 meters?
Yeah, that's a good question. Why 140 meters in size and larger for this next level metric that we're at for determining progress? That's kind of the size, like in doing the hazard modeling and what impact effects could be. There's sort of it's sort of like a knee in the curve. It's where, like, at that point, it's where you could really get not just local but regional impacts, like, let's say, affect like a whole state or a small country, where it could really pose, like for the United States, it could pose a real national security threat to the United States to have such an impact, where it goes beyond like localized impacts. And so it does seem like an odd number, but it's from doing a number of modeling studies of the population and of looking at what the impact effects might be. And certainly we want to find anything that could impact Earth. And as we saw with Chelyabinsk, even 20 meters could do damage. I didn't mention the Tunguska impact over Siberia in 1908. That was probably a 40-meter asteroid that flattened forests. And that's the low end of what we think 2024 YR4 might be. And if that were to impact, it could have been even more devastation from that. But even those were smaller than that 140 meters in size. You could address that. You could, if it's something we couldn't avoid, you could evacuate, you could address that. But as you get larger, the impact effects are a lot higher. So that's really why we want to find anything that's of a size that could do damage, but at least for assessing our progress, that is used because it could pose regional consequences should it impact and not just local.
Any more questions, or we're good here on questions?
Well, Kelly, thank you so much. At the end of the original movie, The Thing, the black and white Thing, there was a reporter that leaned in and on a microphone and warned everyone to watch the skies. And that's exactly what you're doing day in and day out. So thank you very much, more than just for your being here this evening, but for continuing to watch the skies.
Oh, thank you. Thanks for having me. And again, this is kind of a cool case where, astronomy is always important because it's just cool. It tells us about, where we are in the universe, the history of the solar system, the expansion of the universe. There's so much, but it's also something where astronomy can actually be used to protect and defend the Earth. So,
Yes.
so very, very cool. And it's always fun to talk to actual astronomers. And so thank you so much for having me. It's been a
Thank you
pleasure.
very much. Well, I wish you well, and
You're-
thanks again.
All right. Thank you.
Is that it, Lynn?